me here today. So I am the co-founder of Open Bionics. We are a robotics startup based in the UK, in the Bristol Robotics Lab. It's one of the largest robotics research centres in Europe. And I'm going to tell you today about how we're using science fiction to inspire bionics and how we're using robotics to change lives. So I'm going to quickly show you a very short video that was a fan-made video. Someone made it last year, and it went viral online, and it got something like 30 to 40 million views. And it does a really good job of explaining some of our past work. There are hundreds of millions of people around the world who suffer with some form of mobility issue, whether that's being wheelchair bound, having paralysis through their arms from a stroke, or needing artificial limbs. The problem is, exoskeletons and artificial limbs exist, they're incredibly advanced, and they do change lives, but only the few can afford them. You have to be very, very lucky and very wealthy to have an artificial limb. So, we're going to change this, and we're starting with the bionic hand. There are over 11 million upper limb amputees around the world, and when we were doing our first research with amputees, we interviewed hundreds of upper limb amputees, and 96% of them said that a bionic hand would greatly increase their independence and quality of life, and yet the vast majority of the amputees we were speaking with said that they were given through their healthcare services hook prosthetics, or cosmetic hands that have no functionality at all. And the reason that they didn't have the most advanced limb available was because of the expense. So we're going to change how bionic limbs are manufactured. We're going to replicate advanced functionality, but reshape it in a new package. We are also going to make all of our work open source, and we've already started to do this. All of the EMG technology we've developed, the actual mechanical design, everything is online for free and can be downloaded. This is a soldier who lost all of his limbs in Afghanistan. He found our website online and he downloaded one of our first designs and just 3D printed his own hand in his garage at home with his friend. And he lives in the US, we had never spoken before. He just sent us this video of him working with his hand. And people are using our open source work for all sorts of research. Mostly it's in a medical setting, so in hospitals around the world people are using our prosthetics with amputees. But also humanoid robot researchers are using our hands to study human-robot interaction. So when robots are in the home, they can interact safely with us. By using 3D printing, we've made bionic limbs, bionic hands, 20 times more affordable. And this is how we've done this. We've completely changed the fitting process and the manufacturing process. So we use a smartphone or an iPhone. We connect a 3D sensor to the back of the iPhone, called the structure sensor by occipital. We 3D scan someone's limb, or they have a friend 3D scan their limb. Then they email Open Bionics the 3D image of their limb. We then use CAD software to update that limb shape and create a custom socket. This socket takes 48 hours to 3D print. And that in itself is a huge change, is a huge innovation, because to get a custom custom fitted socket as an amputee, it takes multiple appointments, and it takes around 3 months. And it also involves taking a plaster cast. So at the moment, hospitals aren't using these 3D technologies that save time and really improve the experience for the amputee. We also use desktop 3D printers. We don't use really, really expensive 3D printers. The reason why we're doing this is because we want the technology to be accessible to everyone. If we're using affordable equipment, that makes it easier for other people around the world to start innovating and taking our designs and improving them. We also use 3D printed materials that are incredibly light, they're flexible and soft, and they're really durable, they're very strong. One of the super cool things about using 3D printed materials like these is that in the future we will be able to recycle these materials. So children need to update their hand once or twice a year as they grow, and we can just take their existing 3D printed hand and recycle that material and use that material to 3D print them a new hand, so it's saving even more costs. In terms of functionality, we offer the same functionalities as existing bleeding hands. So our hands can open and close, they can perform a pinch grip to pick up tiny objects, a tripod grip, a hook and a point. These functions are the most useful for everyday living for amputees. And the bionic limb is controlled by EMG sensors. So inside the socket, when an amputee puts the socket over their skin, touching the skin are 2 EMG sensors. An amputee just has to squeeze their muscles back and forth, and then they can tell the hand how they want to operate. So far, we're a team of 6 engineers. We've been around for less than 2 years, but we've won a lot of awards. We've been really lucky, and I think the reason why we've received so much attention is because we're thinking about a big problem that a lot of people know about, and we're thinking about solving it in a new way. We're using science fiction as inspiration. So we look to video games. This is one of our first bionic hands. It's from the video game DSX. We teamed up with them to create the Adam Jensen arm. So this is an arm that exists inside a fictional universe by a hero. And we are making these for amputees to wear. And this is the Titan arm. This is inspired by the franchise of the video game. It's strong, it's elegant, it's stylish. It's something that you wouldn't associate with a prosthetic limb. It's not clinical looking, it doesn't look like a medical tool. It looks really fun. And these aren't just pretty renders. We've actually made these bionic devices and fitted them to amputees. So this is Tilly, and Tilly is 10 years old. She lost both of her limbs to meningitis when she was a baby. And this is the most advanced bionic limb she's ever been able to use because they don't make them currently small enough for her. And the difference in psychology is astounding. So when Tilly is given a hook by her hospital, she doesn't want to wear it at school. It causes negative attention and it makes her peers stare. But when she wears this, she's really excited and she feels like she's the hero of a video game. She's the hero of her own life. So it's very, very empowering. This is Tilly's first time using the hand. This is the first object that she picked up. And I just wanted to show you that video so you can see how easy it is for her to use. And it's not just for children, of course, we're making these for adults too. But it's working with children that's one of our biggest passions because children are so underserved in the artificial limb industry because they're not small enough, they're not light enough, they're not advanced enough. So we see ourselves as building the future, turning children with limb differences into bionic superheroes. We think, we will make the bionic industry look like this in the future. So last year, we teamed up with the Walt Disney Company through the Disney Accelerator with Techstars, and we worked with ILM X Labs to create bionic limbs inspired by Disney's best movies. And next year, we're really excited to be able to offer a Star Wars lightsaber hand for young amputees. a Disney Frozen hand, and of course, a bionic Iron Man hand. So we're getting very creative with what bionic limbs could look like, because if you don't have a hand, who's to say that it has to look like a human hand? It can look like whatever you want it to look like. It can have lights, and it can shoot sounds, and it can make you feel great. It can be something special about you. And these are not just toys. Yes, they are very empowering, and they look cool, and they'll make your friends jealous at school. But ultimately, they're robotic tools that enable young children to do more of the activities that their peers can do. So we are really excited about the role robotics plays in our future, and we hope that you are just as excited as we are. And this is just a little taste of what the future will look like. Thank you very much.
Just how cool people found those hands to be. Samantha Payne talked about science fiction, and when it comes to science fiction, few ideas are so enduring as the notion of being able to control external forces, a light switch, a device, through internal brain waves. Enduring, but until now, largely unattainable, at least without invasive surgery that implanted electrodes into the brain. But a research team here in Germany is changing that with a brain-computer interface that, together with exoskeleton innovations, could give hope to millions of people who thought they might never move again. Let's hear more now from Frank Kirchner. He's professor at the Computer Science Faculty of the University of Bremen, CEO of the Robotics Innovation Center, and speaker of the Bremen location of the German Center for Artificial Intelligence, one of the world's largest AI research bodies. A warm welcome to you.
I still have to recover from that last talk. Really inspiring and great work, and it fits really well with what we're probably going to see in the next few slides. We are working on more bulky things, and I think this is the future that we just saw. But in exoskeleton technology, of course, we have to do a couple of steps before we come to a point, as you see on the right side, to have a full body exoskeleton actually that could be used, for example, in the future for rehabilitation of people that have a lesion. The spinal cord lesion can't walk anymore. But we started already in 2008, so over 8 years now, working on this gradually from one-armed exoskeletons to two-armed exoskeletons, and now in the latest version we're working on this full-body exoskeleton, which is dedicated especially to rehabilitation of stroke people, stroke patients, where we have just one arm using for the control and rehabilitation of the movement of one arm, but also in the next step actually to help people that can't walk at all by using integrated biosignal analysis for sensory motor rehabilitation. We're trying to work together in this field because it's a very delicate thing to do and to work with patients, with therapists that can help us to identify what is the correct person, what is the right person, the right patient to use and to start with in order to move slowly forward, because not one patient is identical to another. Everybody has its own story and its own background, and we have to be very careful as tech nerds, not just to cover it all with one big blanket, but to develop technology that is really individual, focusing at each individual person. So that's why we have to have other experts in the field as well. And then we can kick in, and we will have to solve a couple of mechanical problems, like the colleague before talked about control. We also have these problems in the exoskeletons that we want to have smooth, intuitive control, not hard robot-type walking things, but they want to have, of course, systems that can, basically, that they don't feel in the end, that will just support them without actually knowing for the patient that he or she is wearing anything like this. So that means that we have to have a lot of active joints. In this exoskeleton, we will have 32 active drives, plus positive adjustments the whole thing must be self-carrying, because you don't want to carry it around. This patients, they can't carry it around. So it also has to be strong. We need strong motors. We need a lot of power. And these are all mechanical, electromechanical problems that we are now slowly advancing and making advancements and being able to actually do things like in this video, which I hope doesn't show. Actually, well, the video is not put up. Oh, there. Somebody's hitting the right button in the back. Okay, so here you see that the patient also was wearing an EEG cap, like 128 electrodes, and the patient is actually thinking about grabbing this bottle on the screen. And as the system online recognizes this thought, the exoskeleton will then lift the arm of the patient towards the bottle, which is in this case just a virtual bottle, and it will turn green, which means that the bottle, the thought has correctly been identified. So this is what you see here. The movement is a bit fast. That's some things that we have to work on to make it smoother in the control. But what we're focusing on here is to online identify the EEG signal and to grab the correct thought, to grab the correct arm that the patient is thinking about to move. So starting this deliberate movement. We're using two channels, not just the EEG, we're also using the EMG for let's say for safety purposes. We think, or the system thinks, that the patient wants to move the right arm, but then if we see just milliseconds before some small activity in the muscles, then we are sure that we have the right decision taken. So where we are at the moment, we're working on shoulder, we're working on foot elements, we're trying to put in some new innovative things to have the full spherical movement.